In the episode about the Soviet Homeland Air Defense fighters, we have already taken a good look at the fighter variants of the MiG-25. However, the episode did mention that the Foxbat also had other variants designed for different roles. The first half of the video presents these variants, then some urban legends regarding the aircraft's top speed will be debunked, and finally the history of the Soviet MiG-25s in Egypt and a short comparison to the SR-71 closes the topic, at least for now. In addition to the P, PD and PDS Homeland Air Defense fighter variants, there were also the PU and the RU two-seater versions for training. The R and RB were the reconnaissance variants, the BM variant designed to deal with mostly fire control radars of the surface-to-air missile systems. At this point, some enthusiasts of the topic might raise an eyebrow, as many sources list significantly more subvariants with the reconnaissance and bombing capable Foxbat family, such as the RBV, RBT, RBK, RBF and RBS. This is a misconception what is a consequence of their operational use. Documentation issued by the MiG Design Bureau refer only to RB type, which could be equipped with various reconnaissance subsystems. These were listed using Roman numerals from 1 to 5. One such configuration, for example, was the Roman numeral 4, which featured the CAB-3M electronic reconnaissance equipment. However, in the Western English language sources, this configuration was referred to as the MiG-25R and thanks to this designation became widespread, no matter it's inaccurate. The question arises, what was the origin of these designations? In short, the concept was that various reconnaissance modules could be swapped into a given reconnaissance airframe, depending on the requirements of the specific mission. Although in theory the reconnaissance equipment could be exchanged, according to contemporary reports this never happened in practice. The airframes were manufactured with a specific reconnaissance system and they remained in the same airframe until the next modernization. In other words, from an external observer's perspective, the aircraft with a given serial number always had the same equipment package, for example, only the photo reconnaissance equipment. Without proper background information, this was interpreted as, then this is a subtype, while it was simply a reflection of a practical and convenient operational culture. The relationship between designation and operational culture is visible in the way units kept track their aircraft inventory. In the photo, we can see the inventory of a reconnaissance regiment stationed in East Germany. Aircraft with different equipment packages were assigned to the same reconnaissance squadron. The airframes arrived many times with significant time gaps due to manufacturing schedules. The list doesn't show subvariant, it only shows the type of equipment was installed in each aircraft by serial number. For example, aircraft with serial numbers 53, 55, 56 and 57 had the Cyrillic letter B, which phonetically corresponds V in English, indicating the virile system. There is no mention of any RBV variant, as it was called by Western sources. Although, as was mentioned, every recon airframe was either an R or RB variant, this video still includes the incorrect Western designation purely for easier comparison with other sources. Production of another major branch of the MiG-25 family ramped up slowly. The R variant, suitable only for daytime photography, was produced for just 1 year in 1969. The RB variant, capable of nighttime photography as well, was manufactured between 1970 and 1980. A total of 220 R and RB aircraft were built over the 12 years, meaning they were produced at an average rate just 18 aircraft per year, less than 2 airframes per month. To put this production pace into context, 205 Su-27 fighters were built in just 1986 and 1987 alone. In the late 70s and early 80s, the United States produced between 12 and 18 F-15 fighters per month, roughly the same number in a single year as total number of MiG-25 RBs ever built. This clearly shows that the production rate of the reconnaissance aircraft was at a completely different level compared to the fighter jets. Understanding the capabilities of a specific MiG-25 configuration is easier if we know where each subsystem could be placed and the space was occupied. The nose section of the MiG-25 can be divided into 3 major compartments: The first spans from the frame numbers 1 to 7, the second from frames 7 to 10, and the third from frames 10 to 16, which is essentially the first fuselage frame. In addition, equipment required for specific missions could also be installed in compartments below and behind the cockpit. What a particular MiG-25 reconnaissance variant was capable depended on both its subvariant and the type and configuration of equipment it carried. The MiG-25R, the Product 02, was suitable for daytime photography and electronic reconnaissance. The front section of the nose, the space between fuselage frames 1 to 7, was empty. Just behind it, it could carry either the SRS-6 Romb-4A or the SRS-7 Romb-4B electronic reconnaissance system, and in the rear part of the nose section, either the A7M or the A72 camera. Beneath the pilot's instrument panel was the AE/10 camera compartment. It's important to note that not only the RB, but also the initial R variant, the reconnaissance equipment, was never swapped. Each aircraft was manufactured with either the A7M or the A72 camera, and one of the Romb-4 variants, and remained the same until the next upgrade. Since this version was produced for barely a year, it can be considered as a pre-series. Only a few airframes were built in each configuration. Let's look at the main characteristics of the specific subsystems. The A7M camera was designed for photographing larger areas with lower detail, while the A72 was suitable for capturing smaller areas with higher resolution. The A7M weighed 390 kg and the A72 was lighter, it weighed only 280 kg. In addition to these options, the AE/10 system was permanently installed alongside both cameras for topographic photography. This equipment weighed 73.5 kg. With the A70M camera, the photographed area was approximately 100 km wide. The system had 4 cameras with a 44-degree field of view of each, providing a total effective viewing angle of 140 degrees, while avoiding distortion at the edges of the optics. It used a 30 by 50 cm film and could take 432 images. The resolution of the photograph ranged between 1 and 10 meters. The A72 system photographed a 10 km wide area. It had 2 lenses with a 20-degree field of view, resulting in a total effective viewing angle of 32 degrees. The maximum achievable resolution was around 30 cm. These 2 cameras were controlled by the Peleng-D system, which handled exposure automatically, at least that was the concept. The AE/10 topographic camera could only take 60 images on an 18 by 18 cm size film. Its resolution ranged between 3 and 5 meters, and it photographed on an area 20 km wide. The 2 electronic reconnaissance equipment operated in different bands. The SRS-6 operated in the 3 cm band, while the SRS-7 was suitable for detecting radars in the 10 cm band. This system could identify the radar type, estimate its location, and determine the duration and timing of the aircraft exposure to radar signals. The SRS-6 was divided into 34 channels and the SRS-7 into 18 channels, with each channel receiving signals within a specific frequency range and recording them onto film. The data collected could be only analyzed after landing. This system could only gather signals from the left and right directions. Front and rear areas were off limits. Another limitation was that it could only detect pulse mode radars. It could not handle continuous wave radars. The latter waveform time is used, for example, by the fire control radar of the Hawk air defense system. High-speed and high-altitude flights made the use of autonomous navigation support system a necessity. Flying an aircraft at an altitude of 18 between 20,000 meters and the speed of 700 meters per second or higher using only a stopwatch and compass could introduce such a level of inaccuracy into the flight path that photographing the target might not be guaranteed, especially if the goal is to capture detailed image using a narrow field of view camera. With a speed of roughly 700 meters per second, the aircraft flies 7 kilometers in just 10 seconds. At very high altitude and speed, navigation based on visual reference points is inherently impossible. The A72 camera, even at 20,000 meters of altitude, had a field of view only ±5 kilometers. So if the navigation accumulates just much error by the time the aircraft reaches the target area, and the photo is taken between 10 and 15 seconds later, even in salvo mode, capturing many photos in series, the desired object might not appear on the images at all. For this reason, the MiG-25R was equipped with the, in principle, revolutionary Peleng-D digital inertial navigation system. However, the system operated with such a low reliability that in practice it was nearly unusable. Its central component was the Orbiter 1-155 digital computer, which used magnetic ring memory blocks. Loading the coordinates of waypoints into computer's memory was done using a copper wire and a wooden needle, which were used to thread the wire through the magnetic core memory rings that store the coordinates. This process could take up to 4 hours. It required a specially trained technician to perform. In practice, the Peleng-D system was highly sensitive to temperature changes, which frequently caused malfunctioning during flight. Eventually, operators received special equipment for repairing the computer. But even with this support, operational reliability remained very poor. At one unit, over a 6-month period, only a handful of flights could be conducted in automatic mode. As a result, the Air Force Technical Service essentially banned the use of the Peleng-D system. Thanks to this, the reconnaissance equipment had to be operated manually, with all the disadvantages what was explained previously. The MiG-25R was essentially just a pre-series model which revealed which parts of the concept were viable and which were not. The platform itself was adequate, but the aircraft still struggled with serious shortcomings in other areas, especially in navigation equipment. As usual, the next member of the MiG-25 family, the MiG-25RB, the product 02B, was developed using the experience gained from the pre-series airframes. The MiG-25RBs were produced between 1970 and 1980. It could be equipped with 4 different reconnaissance equipment packages. The manufactured airframes between 1970 and 1972 were also suitable for nighttime reconnaissance. These had the Mk-75 camera, designed for night photography, installed in the rearmost compartment of the nose section. They could carry the FOT AB100-140 illumination bomb. The maximum loadout was 8 bombs. The Rombo-4 system also was installed in the same 2 configurations as happened in the earlier R variant. Another difference was the introduction of the SPS-141 electronic jamming system, which was built into the very front section of the nose. The B letter in the designation indicated that aircraft's ability to carry bombs. In addition to illumination bombs, it could carry conventional FAB 500M-72T bombs or the RN-28 nuclear bomb. Conventional bombs had to withstand the heating caused by the speed of Mach 2.35 for 15 minutes. The bomb itself could handle more, but the fuse was the limiting factor. This is what the T in the designation refers to, thermostoikaya, meaning heat resistant. With a nuclear bomb, the aircraft's maximum speed was significantly restricted. The NAFA Mk-75 system, capable of nighttime photography, weighed 275 kg. When the plane carried illumination bombs, the maximum speed was limited to Mach 2.25, and even that could only be maintained for 12 minutes. Airframes supported with the Mk-75 system were listed in the operational manual as variation-free of the RB, with the difference being that instead of the ROMB system, they were fitted with the VIRA system, see later. The bomb loadout varied depending on the specific MiG-25 variant. Initially, the MiG-25RB could be equipped with 4 MBDZ-U2 bomb racks. 2 under the fuselage and 2 under the wings, each capable of holding 2 bombs per side, allowing for a total bomb load of 4 tons. However, due to the induced stress on the wings, this maximum load was later reduced to 2 tons, and bombs could be carried only under the fuselage. This restriction was eventually lifted with the introduction of the modified MBDZ-U2TK bomb racks. These new racks allowed for tandem bomb mounting and a revised release sequence, enabling a bomb load of 4 tons again. Following the overhauls in the early 80s, the maximum load was increased to 5 tons. Interestingly, despite its bombing capability, the MiG-25RB did not have a bomb sight. Bombing was carried out solely with the help of the Peleng D navigation system. Essentially, the pilot was bombing blind, and the inherent inaccuracy of the navigation system always introduced errors. As a result, the MiG-25RB was effectively only suitable for nuclear bombing. From an altitude of 20,000 meters, the dispersion of conventional bombs was on the order of 1.4 kilometers. If the navigation system failed, even the effective use of nuclear bomb became questionable. In addition to the expansion of reconnaissance equipment, the RB variant could be equipped with electronic jamming systems, more exactly with the SPS 141, 142 or the 143 variants. These could jam in 3 different wavelength bands, 3, 4 and 5 centimeters. The jamming program could be set only on the ground before the flight. The available options were as the follows. Against pulse mode radars, the system used inverse gain or sliding frequency jamming, depending on the selected program, to distort the distance and angle readings. Against continuous wave and quasi-continuous wave radars, 2 programs were available. For self-defense, it used Doppler jamming to distort speed and sliding frequency jamming to distort angle. For protecting formations, it used flashing Doppler noise jamming. The jamming coverage in azimuth was ± 60 degrees and in elevation ± 30 degrees, but only forward direction. Given the MiG-25 speed, jamming to the side or rear was pointless. The photonic adjacence variant was equipped with the SPS 141 jamming system, designed to counter fire control radars, as it was intended to fly over hostile territory where enemy surface-to-air missile systems were expected. Against pulse mode radars, like the fire control radar of the Nike Hercules, it was simultaneously performed angle and distance deception jamming that distorted both measured distance and angle. Against continuous wave radars, like the fire control radar of the Hawk, or quasi-continuous wave radars like those used by the Patriot system, it was capable of self-defense using similar jamming techniques, or even protecting larger formations with flashing Doppler noise technique. In the latter case, 2 or more jamming aircraft were required to protect the formation. The method did not work with a single jamming source. The effectiveness of jamming against systems like Nike Hercules, Hawk or Patriot remains an interesting question because it was never performed in combat, but the reconnaissance aircraft were prepared to counter these threats. The mass production of a larger portion of the MiG-25RB started in 1973 in several different configurations as shown in the manual referenced at the beginning of the video. According to the operational manual, aircraft equipped with the configuration packages 1 and 2 were suitable for daytime photo and electronic reconnaissance, but they were already fitted with the SLS-9 Virage 1 system, which replaced the earlier ROM-4 system. Additionally, the nearly unusable Peleng D navigation system was replaced with the more reliable Peleng DM. The level of inaccuracy, the drifting of the Peleng navigation system was roughly halved, and thanks to the new electronic memory, which replaced the magnetic ring memory blocks, programming the system took only 15 to 20 minutes instead of 4 hours. Despite having the same designation, the early small series RB variants, which were manufactured between 1970 and 1972, had a different navigation system than the later widely produced airframes. The Virage 1 system was capable of electronic reconnaissance up to approximately 450 km in left-right directions, but it could not receive signals from a ± 35 km wide strip directly beneath the aircraft. The accuracy of distance measurement of detected emitters was in the 13–15 km range. The Virage 1 weighed 186.5 kg, and in addition to the pulse mode radars, it was also capable of detecting continuous wave radar signals. Airframes equipped with the Virage 1M system were produced between 1973 and 1980. In the West, these were mistakenly referred to as MiG-25RBV subvariant. It's important to note that regardless of configuration, all RB variant airframes could carry both conventional and nuclear bombs. Airframes manufactured between 1973 and 1980 were also equipped with the SRS-10 Cube-3M electronic equipment, which also got the newer Peleng DM navigation system. The Cube-3M occupied in the middle and rear section of the nose compartment, and did not include the AE/10 topographic camera. These aircraft were fitted with the SPS-143 electronic jamming system. The reason for the different electronic jamming system was that these aircraft were not intended to fly near surface-to-air defense missile systems, as they could detect enemy radars from a distances between 45 and 450 kilometers. No Western air defense systems at the time could shoot down such a high-speed cross-flying target from such a long distance. The SRS-10 could detect both pulse and continuous wave radars and determine the radar's operating mode, location, pulse duration and pulse repetition frequency. The position of detected radiation sources was based on navigation data from the PLANC-DN system, with an accuracy ranging between 2 and 10 kilometers. The system could only receive from one direction, either from left or right. The minimum detection range was 45 km and the maximum was 450 km when flying at an altitude of 20,000 meters. The collected data was digitally recorded and transmitted via data link to a ground station even up to 1,500 km, which made near real-time processing possible. The COB-3M had a mass of 520 kg. The SPS-143 and SPS-142 jamming systems were primarily used for training against their own air defense missile systems. The SPS-143 was used for jamming S-75M Volkhov, while the latter was used for jamming Neva, Vega, Krug and other Soviet fire control radars during exercises. The MiG-25R often served as a training target within the Warsaw Pact. These aircraft flew with Configuration 4, which were mistakenly referred in the West as MiG-25RBK. Airframes manufactured between 1973 and 1977 were equipped with the RSR-2 Sabre side-looking reconnaissance mapping radar and the SPS-142 electronic jamming system. The Sabre system was 400 kg. It operated in the centimeter wavelength range. It could map a 25 km wide strip located between 45 and 70 km from the side of the aircraft with a resolution of approximately 30 meters. This allowed only large static objects to be identified. The radar was used only at flight altitudes between 17 and 24,000 meters. The system had quite an interesting technology to store data, a true Soviet-style one. The signals received by the radar were displayed on a cathode ray tube, essentially on a TV screen. This screen was photographed by the equipment onto conventional film reels. They could be analyzed on the ground using special equipment. A photo was taken every 12.5 km flown section, recording the aircraft's current position and heading from the navigation system. This was the configuration marked with Roman number 5 of the RB airframes, which was mistakenly referred in the West as MiG-25RBS variant. The MiG-25RB type underwent modernization, which essentially involved replacing the equipment within each configuration and included some other upgrades either. However, even after these upgrades, the aircraft designation was not changed. The equipment replaces took place between 1980 and 1982 as follows. The Viral system was replaced by Tangage on aircraft with Roman numeral 1, 2 and 3 configurations. The photographic reconnaissance equipment remained unchanged. These aircraft were mistakenly referred in the West as MiG-25RBT. On airframes with Roman numeral configuration 4, the COB-3M electronic reconnaissance system was replaced by the SHAR-25B. These airplanes were mistakenly called MiG-25RBF in the West. On airframes with Roman numeral configuration 5, the Sabre mapping radar was replaced by the SOMPOL system. These were mistakenly referred to MiG-25RBS in the West. All airframes received the new Orbita 10-155 onboard computer, and the PLANC-DM navigation system was replaced with the more advanced PLANC-2, which had half the drifting error compared to the DM version. Additionally, they were equipped with the SPO-15 radar warning receiver. Its antennas were installed on the side of the air intake. The maximum bomb load increased to 5,000 kg thanks to the MBD-3-U2 bomb rack mounted under the fuselage. Let's see in short one by one the capabilities of the new equipment. The Peleng 2 navigation system could achieve positional accuracy within ± 20 meters in target area if it could receive coordinate corrections via long-range radio link, though this link was susceptible to jamming. The SPO-15 radar warning receiver could identify threats based on different radiation patterns, prioritize them, and display the bearing the two most dangerous. In the forward airspace, it could differentiate sources within sectors approximately between 10 to 40 degrees wide and detect whether a source was coming from the rear left or the rear right. It could detect radars with low and medium pulse repetition frequencies, as well as continuous wave radars. For example, it could distinguish any kind of pulse radar from a continuous wave fire control radar, like the fire control radar of the Hawk system. The Tangas system offered more accurate position measurement, with an error of margin between 10 to 30 km. It eliminated the blind zone beneath the aircraft and could detect quasi-continuous wave radars either. However, it still recorded data on magnetic tape, just like the earlier Virage 1 system. The Char 25B system had capabilities similar to the Cube 3M, but it was more advanced in terms of radio-electronic complexity. It could provide information even in environments affected by electronic jamming. Additionally, it could detect quasi-continuous wave radars, such as those used by the American Patriot air defense missile system, which appeared in the early 80s. Like its predecessor, this variant could transmit collected target coordinates via data link. We can say that two-tier electronic reconnaissance capability existed both before and after the modernization. Before the upgrade, Virage 1 represented the basic capability, while the Cube 3M was the high-end system. The basic electronic reconnaissance system could be installed alongside photo reconnaissance equipment, but the high-end system could not. The basic package had lower accuracy and recorded data on magnetic tape, while the high-end system could transmit data via data link during flight for real-time analysis. After modernization, Tangas and Char 25B became the new basic and high-end system respectively. The first generation electronic reconnaissance equipment could only identify pulse radars, while the Virage and Cube could detect continuous wave radars, and Tangas and Char 25B could detect quasi-continuous wave radars as well. The radar-based mapping, the SOMPOL system had 3 times better resolution than its predecessor, the Sabre offering an average resolution of 10 meters. Additionally, it could be used not only at high altitudes, but across a wide range between 300 and 23,000 meters. However, it could distinguish moving objects from stationary targets. The aircraft cockpit also changed after modernization. The upgraded cockpit is easily recognizable by the display panel of the SPO-15 radar warning receiver. The last produced variant of the MiG-25 family was the MiG-25BM, the Product 66, developed specifically for engaging the radars of air defense missile systems. More precisely, the emergence of the American Patriot air defense missile system was the drive behind the design of the new subvariant. Earlier anti-radar missiles had too short range to be launched from outside the Patriot's engagement zone. Moreover, the older and slower anti-radar missiles could be intercepted by the Patriot thanks to its multi-target channel capability. Between 1982 and 1985, only 40 MiG-25BM airframes were produced, making it the least produced combat variant of the MiG-25 family. Due to its specialized role, the equipment housed in the aircraft nose section differed from the RB variants. Between frames 1 and 7, the SPO-151OZ Sirene 1D jamming system was installed. Between frames 7 and 10, the Jaguar radar detection and target designation complex was installed, including the SICH-M receiver with protruding antennas mounted on the sides of the nose to allow forward receiving even behind the electronic jamming system. At the rear of the nose section, the side-looking Tangas electronic reconnaissance package, the SRS-13, was installed. This was also installed on some RB variant airframes. The aircraft was equipped with a modified Peleng navigation system, the Peleng 2M, to support specific operational modes of the anti-radar missiles. The Jaguar system included the targeting unit, electronic jamming equipment, and the KH-58U anti-radar missile. Using the Jaguar targeting complex, the SICH-M receiver, and the passive seeker head of the KH-58U missile, the system provided the following capabilities: searching and detecting radars, analyzing and prioritizing detected targets and assigning them with the missile seeker heads, determining target data and transmitting into the digital computer to calculate launch distance, and finally transmitting data to the missile for computing its quasi-ballistic trajectory. Despite its external differences from earlier variants, the MiG-25BM had its nose painted grey, similar to fighter versions, to resemble them more closely, especially since it also featured 4 underwing hardpoints. The only reason was to fool the Western intelligence agencies about the role of the new planes. The BM version could also carry a drop tank under the fuselage, just like the Recon variant. Like the RB family, the BM could carry up to 10 from the same special thermal protected FOB 500 bombs and the RN-28 nuclear bomb, even though none of them was its primary armament due to its specialized mission. Its main weapon for destroying or disabling radars was the KH-58U with NATO codename AS-11 Kilter missile. The base KH-58 was originally designed for the Su-24, but the MiG-21 required different tactical solutions due to its high-speed operational profile. Flying at Mach 2.35 and launching from altitudes around 20,000 meters, the missile reached about Mach 5 burnout speed, requiring a missile body capable of withstanding of temperatures about 400 to 500 Celsius. The base variant of the KH-58 was limited to a launch speed of Mach 1.5. For the KH-58U, the wings and control surfaces were entirely made of welded titanium. The fuselage was made of steel and included internal thermal insulation to protect internal compartments. Compared to the base version, the KH-58U featured a dual thrust rocket motor. The engine during the boost phase provided 6 tons of thrust for 3.6 seconds, accelerating the missile from Mach 2.35 to about Mach 3.6, then followed by a 1-ton thrust phase for 15 seconds. Power supply was ensured by a high-capacity nickel-cadmium battery, lasting at least 200 seconds. After launch, the missile flew a quasi-ballistic trajectory, which kinematically allowed a launch distance up to 300 km. It must be noted that in such a long-range launch, onboard power supply was not guaranteed. Nevertheless, during acceptance tests, hits were recorded even at such distances. The exceptionally high speed and high launch altitude made it possible to achieve this remarkable feat. For comparison, even when launched at 10,000 meters of altitude at Mach 0.9, the contemporary American AGM-88R missile did not have a range of 100 kilometers. However, the Soviets quickly realized that producing only for the 40 MiG-25BM airframes, the KH-58U would be impractical. As a result, the U variant was later adopted for use on the Su-17 and the Su-24, though with significantly reduced range. At low altitude and subsonic speed, its range was limited to 40 km, and at high altitude increased to 70 km. In the missile's designation, the U stands for universal, indicating that multiple aircraft types could carry it. However, from a radial electronic perspective, it was not universal. The KH-58U could be equipped with 4 different seeker heads, each tailored for a specific target type. One seeker type for the Hawk's fire control radar, one for the Patriot's multifunction radar, one for centimeter wavelength target acquisition radars, and one for decimeter wavelength radars. Each KH-58U missile was individually programmable, allowing an aircraft to carry multiple missiles without different seeker heads simultaneously. In contrast, the American AGM-88R missile could engage any radar operating between 0.5 and 20 GHz, but only from much shorter distances. No matter the shorter range of the AGM-88, its operation flexibility in the 80s was unparalleled. Launch weight of the KH-58U missile was 650 kg, with a warhead weighing 149 kg, of which 58.5 kg was explosive material. It featured a laser proximity fuse detonating either 5 meters above the ground or target, or upon impact. Ideally, the MiG-25BM performed its mission after a reconnaissance flight by an RB variant equipped with specialized electronic reconnaissance system, CUB-3M, or with the SHAR-25B. However, since the BM also carried the Tangar system, another BM aircraft could perform basic electronic reconnaissance if it was needed. It's worth saying a few words about the range of the specialized versions, which differed significantly from the fighter versions thanks to three main factors. The MiG-25 fighter had to reach high altitude as quickly as possible to intercept high-speed targets, so it used its engines on full afterburner power from takeoff until reaching about 18 to 20,000 meters. With the drag of 4 large R-40 missiles, it had only 400 km combat radius. In contrast, the R, RB and BM variants did not require time-critical climbs, so they climbed to 11,000 meters at subsonic speed using only military, non-afterburning power. Only above this altitude did they engage maximum afterburner for acceleration and further climb. The R, RB and BM variants could carry external fuel tanks under the fuselage. While later manufactured modernized fighter variants could also carry them, they used them only for ferry flights. Reconnaissance variants could use the tanks during the subsonic climb phase, giving them more fuel for supersonic dash and climb above 11,000 meters. Before the acceleration, the drop trunk was jettisoned. During a fuel-efficient subsonic climb, followed by the acceleration above 11,000 meters of altitude, the reconnaissance variant consumed 5.7 tons of its 15-ton internal fuel load, 40% of the internal quantity. In contrast, the fighter version would have already burned 8.5 tons, 60% of its onboard fuel by that point. Reconnaissance variants did not carry external stores, therefore they could reach Mach 2.35 at an altitude above 17,000 meters with less thrust and more quickly. Mach 2.35 was the practical supersonic speed used by both the fighter and R, RB and BM variants. Due to these differing operational parameters, the MiG-25RB had a combat radius of 920 km with drop tanks, which is 2.3 times greater than the fighter variant, even with the same Mach 2.35 cruising speed. Without drop tanks, its range was 680 km, still 70% higher than the fighter's high-speed interception profile. With 4 500 kg bombs, the range dropped to 560 km. With the subsonic profile flying between 9 and 10 km of altitude at Mach 0.9, the combat radius was 1040 km with drop tank and 770 km without drop tank. Compared to the fighter variant, the internal fuel capacity increased from 14.2 tons to 15 tons. It is important to consider the listed combat radius values as a base for total distance flown by multiplying them by 2. While the fighter variant typically flew to a point and returned, the reconnaissance variants flew over or near the target area in a wide, low G-arc, maintaining speeds above Mach 2 to ensure sensor effectiveness and survivability. Thus, after climbing and accelerating within friendly airspace, the high-speed segment of the mission was typically flown over hostile territory, and ingress was also performed at high speed, followed by deceleration only after exiting the threat zone. This will be illustrated with examples from the Middle East deployment. Before diving into MiG-25's Middle Eastern history, it's worth clearing up some widespread myth about its top speed. As previously was presented in the series of Homeland Air Defense fighters, while the MiG-25 theoretically could reach the often quoted Mach 2.83, but this was only possible without carrying weapons. With 4 R-40 missiles and climbing to around 20,000 meters, the aircraft reached Mach 2.35 at the end of the climb using full afterburner, which took about 13 minutes. While the aircraft could have accelerated further, the maximum allowed duration for full afterburner was only 15 minutes. It's also important to note that this 15-minute limit was reached only gradually. In 1969, when the pre-production series entered service, the limit was only just 3 minutes. By 1971, it was increased to 8 minutes and eventually to 15 minutes, which remained the standard through the aircraft's career. However, this duration limit applies under standard atmospheric conditions. Temperature variations due to the seasonal changes and latitude also affect performance. So let's explore the structure of the atmosphere to better understand its impact on top speed. Two layers of the atmosphere are relevant in this case, the troposphere and the stratosphere. The troposphere behaves in a way that is logical to an average person, as it is layered directly above the Earth's surface. It is warmer near the equator because the amount of solar radiation per unit area is higher there than it's further north or south. Solar radiation heats the Earth's surface, and since dry air behaves almost like a vacuum in terms of radiation, the heat is transferred into the atmosphere through heat conduction and convection. This is why we observe the basic phenomenon that in the troposphere, temperature decreases with increasing altitude by approximately 5 degrees Celsius per 1000 meters. However, this temperature decrease continues only up to the tropopause, which separates the troposphere from the stratosphere above it. The part of the stratosphere is the ozone layer, which absorbs UV radiation from the sun. As a result, in this region the atmosphere begins to warm again as altitude increases relative to Earth's surface. So far, this is straightforward. Because the Earth rotates, the tangential speed increases approaching to the equator, which also increases the centripetal force acting on the atmosphere. As a result, the atmosphere is thicker at lower latitudes, meaning that the troposphere is also thicker, therefore the ozone layer is at higher altitudes. This allows the troposphere to cool further, since warming only begins at higher altitudes. Near the 30th parallel, for example in Egypt, warming of the stratosphere begins only about 25,000 meters, whereas further north, such as the 70th parallel near Murmansk, it starts already at 10,000 meters. This is a considerable difference. Therefore, even though the surface is generally warmer at lower altitudes, the temperature at the top of the troposphere above Egypt and Israel is lower than the Arctic regions of the former Soviet Union. The farther south we go, the colder the stratosphere becomes, which is the opposite what would seem logical, but only within certain altitude ranges. The consequence of this, while at 20,000 meters over Murmansk the average temperature is minus 49 Celsius, over Egypt it is minus 70 Celsius. The ICAO standard, the atmosphere, defines the minimum stratospheric temperature as minus 56 Celsius. Due to the lower stratospheric temperature, the airflow around the airframe and the intake air to the engine is also colder, which improves cooling of the aircraft and turbine blades. It reduces the final compressor temperature in the compressor compared to the standard atmosphere. Consequently, the use of full afterburner could be extended from 15 minutes up to 40 minutes. Every flight that deviated from standard operational procedures had to be personally approved by the Soviet Minister of Defense. Thanks to this, the MiG-25R could fly at the Middle East at 22-23,000 meters of altitude, while in the Soviet airspace the typical maximum altitude was between 18 and 20,000 meters. Also, the fuel consumption of the plane was better, so it could sustain longer the high speed, or the maximum speed what could be sustained also was higher. Moreover, the reconnaissance variant, thanks to their subsonic climb and drop tank, had more fuel to utilize the longer allowed afterburner use. In fact, not only Soviets, but some Western pilots also experienced this strange behavior of the atmosphere in a different airplane. More about this topic in the extra content. The top speed of the MiG-25 was primarily defined by the overheating of external stores. Various external stores limited the top speed of both the fighter and reconnaissance variants of the MiG-25, as well as how long those speeds could be maintained. With the FOTAB illumination bomb, flying speeds between Mach 2.1 and 2.25 was limited to 12 minutes due to the risk of the bomb's fuse overheating. With the 500 kg special thermal protected fragmentation bombs, flying at Mach 2.35 was limited to 15 minutes, again due to the fuse overheating. The MiG-25BM was limited to Mach 2.35 when carried Kh-58U missiles. For the fighter variants, carrying any type of the Air-14 limited the airplane to Mach 2.35. Moreover, missiles could not be mounted anywhere. On the outer pylons, the missile noses would heat up to 300 degrees Celsius, so infrared guided versions could be only carried on the inner pylons during high-speed flights. When the fighter variant carried R-60 missiles, Mach 2.35 could only be maintained for 2 minutes and Mach 2.2 for a maximum of 8 minutes. The R-60 was designed for frontline fighters for maneuvering close air combat, which take place at subsonic speeds. As a result, the R-60 had no thermal protection, and due to its smaller size, it heated up more quickly. The heating of the airframe also restricted the duration of the high-speed phase. The MiG-25 used a special T6 type of kerosene, which had a self-ignition temperature of 220 degrees Celsius in the fuel tanks. At Mach 2.65, certain parts of the airframe heated up to 250 degrees Celsius, and at Mach 2.83 up to 290 degrees considering standard atmosphere. Therefore, under standard atmospheric conditions, speeds between Mach 2.65 and 2.83 could only be maintained for 5 minutes, and flying faster than Mach 2.65 was prohibited during peacetime. Flying at Mach 2.83 required special authorization from the MiG Design Bureau. During functionality check flights following an overhaul in the Cold War era, acceleration up to Mach 2.65 was permitted. However, following an accident in 1991, the limit was reduced to Mach 2.35. It is not an overstatement to say that the often quoted Mach 2.83 top speed of the fighter variant is theoretical. Its armament simply did not allow higher speed than Mach 2.35. Sensationalist articles and videos that claim that the fighter variant could reach Mach 2.83 or claiming such funny things that it could sustain Mach 3 can be simply ignored. In practice, this was impossible without overheating the electronics of even the heat-insulated R-40 missiles. In fact, due to the drag of the missiles, the aircraft couldn't even reach such speeds before running out of fuel. The top speed of the MiG-25 reconnaissance variant is a fertile ground for exaggerated, we can say, fishing stories, since it was not limited by aerodynamics or engine thrust if did not carry external stores. One thing is sure, the Design Bureau provided duration for each speed where fuel tank self-ignition would not occur with a nice safe margin. Whether Volodya or Sergei may have exceeded these limits under unusually cold stratospheric conditions and reach or surpass Mach 3, well, in theory it's possible, but it cannot be reliably verified. Only radar operators and their reports from that time could confirm such claims. In any case, this would not provide real tactical significance. More about this in the extra content. The first operational deployment of the MiG-25 took place in the land of the Faroes in 1971 and 1972. In the spring of 1971, 4 MiG-25s, reportedly 2R and 2RB variants, along with radio tactical and maintenance equipment, were airlifted to Cairo West Airport. This transfer required 4 AN-22 and 56 AN-12 transport flights. The aircraft were delivered directly from the factory airfield in Gorky. The assembled aircraft had no identification markings or insignia. Following the assembly, the functionality test flights were performed by the test pilots of the Gorky aircraft factory. Between 1971 and 1972, the recon aircraft carried out roughly a dozen reconnaissance missions flown by the Soviet pilots. To ensure mission reliability, reconnaissance flights were typically conducted in pairs in case one aircraft experienced technical failure. The pair of aircraft flew with 30-second interval between them, so that if Israel had any effective means of shooting them down, they would not be able to target them one after another using single target channel surface-to-air missile systems. Interestingly, it was authorized to perform dynamic climb if a missile had been launched at them. They could use their momentum to climb to altitudes up to 30,000 meters. This permission was interesting because the MiG-25s did not have radar warning receiver at the time, and detecting visually a missile launch was impossible. During mission planning, the idea was raised to flying over Israeli territory, then landing with the planes in Syria, but this was ultimately rejected. Missions could only be launched from Egypt, and the aircraft had to return there. Since the MiG-25 required extensive maintenance and their used special T6 kerosene, the fuel would have needed to be stored at more locations, more logistical challenge. Eventually, because political reasons, the Soviet leadership only authorized overflights of the occupied Sinai Peninsula, entering Israeli airspace was not authorized, which rendered the idea entirely impractical. The MiG-25 unit represented only a small fraction of the Soviet presence. Under the framework of Operation Caucasus, the 11th Air Defense Division deployed to Egypt with 3 brigades comprising a total of 24 short-range S-125 Neva surface-to-air missile batteries. The Soviet Navy was also present in the region, operating Tu-16P, IL-38 and AN-12 aircraft. In the ports of Alexandria and Port Said, ships and support units of the 5th Mediterranean Operational Squadron were stationed. Within the Ministry of Defense, staff and the central apparatus, around 3,000 Soviet military advisors and specialists were part of the organization. Altogether, approximately 35,000 Soviet troops were stationed in Egypt during this period. The first reconnaissance missions aimed to photograph the Sinai Peninsula, which had been occupied by Israel following the 1967 Third Arab-Israeli War, also known as the Six-Day War. The Israelis built strong defensive lines there, with forward position extending to the banks of the Suez Canal. Further east, the first and second defensive lines were located at depth of 50 kilometers or even more. The first mission was carried out on the 7th of August 1971 along the edge of the occupied territories, essentially flying from south to north along the Suez Canal. According to the intercepted Egyptian air defense communications, the Foxbat pair crossed the canal near Dever Soar and passed about 13 kilometers east of Port Said. The pair flew approximately 65 kilometers northward, then turned west and returned to the Egyptian airspace between Baltim and Alexandria. Another Foxbat pair, about 5 minutes behind the first, was tracked as far as Abu Zanima area, where tracking was lost. They were later detected again by radar as were flying north along the canal. When the first area photographs were presented to the Soviet and Egyptian leadership, everyone was surprised by the excellent image quality. Fortifications, bunkers, tanks in entrenched position, communication networks, vehicles and other features on the Sinai Peninsula were clearly identifiable. Using the ROM-4 electronic reconnaissance equipment, air defense radars, anti-aircraft positions and airfield radar installations were successfully mapped. On the 10th of October 1971, a pair of MiG-25 approached Tel Aviv. The pair of MiG-25 arrived from northwest, then they turned back to the west near Haifa, then followed the coastline back towards Port Said when they re-entered Egyptian airspace. However, due to a navigation error, one of the aircraft briefly entered in Israeli-controlled airspace. It was only 29 kilometers from Tel Aviv instead of the permitted 40 kilometers. This incident was an indication how a malfunctioning or unreliable navigation system could cause significant deviation from the planned flight path. The repeated overflights above the Sinai Peninsula reconnaissance missions effectively laid the groundwork for operational planning to next war. The analysis of the photographs enabled the Egyptians to destroy the Israeli Bar-Lev fortification system during the Yom Kippur War with relatively few casualties. The Egyptians knew exactly where the artillery positions and ammunition depots were located behind the Bar-Lev line. Such preparation would have been impossible without active Soviet involvement. The Israelis could have intercepted a MiG-21 or any other reconnaissance aircraft, and those aircraft would not have been able to photograph such a large area with just a few flights. The first reconnaissance mission was flown on 17 August 1971 and the last on 16th of May 1972. The high-resolution mapping photographs were essential for planning, as at the time only such photo-recon satellites existed, which had to reject film capsule back to Earth. The delay was long, the process was very complicated, and the trajectory of the satellites seriously restricted their use. The first satellite capable of transmitting digital images, the KH-11, was launched in December of 1976. But that was an American satellite, something that Soviet Union could not even dream of at the time. The Soviet equivalent, the Yantar 4KS-1, was launched in 1982, but only became fully operational in 1985. Thus, the MiG-25RB represented the pinnacle of the available aerial reconnaissance technology of the Soviet Union at the time. During the deployment of the MiG-25s, the question their protection arose. Since during the War of Attrition, the period between the Third and Fourth Arab-Israeli Wars, the Israeli Air Force regularly attacked Egyptian airfields. Therefore, it was determined that concrete shelters should be built for new and extremely expensive aircraft. These shelters were ultimately constructed in an improvised manner, essentially with on-site engineering. The structures were concrete bunkers. The entrance was protected by strong steel doors filled with sand. Each shelter had two exhaust outlets at the rear. The engines could be started inside, allowing system checks to be performed inside the shelter. Following the checks, the planes could immediately taxi to the runway and take off almost instantly, minimizing the risk of being destroyed on the ground by Israeli forces. An interesting aspect of the MiG-25's Middle Eastern deployment was what the crews considered as a threat. It wasn't the aircraft's speed that was decisive, but rather its altitude. They flew well above the engagement zone of the American Hawk surface-to-air missile system used by Israel, which was around 18,000 meters. However, reaching such altitudes requires high speed. There was also concern that Israel might use a captured SA-75 Dina-Soviet SAM system from the Six-Day War, which could potentially shoot down the MiG-25 despite its high speed and altitude of around 20,000 meters. Today we know this was not a real threat. Interestingly, it was considered that Israel might secretly deploy an American Nike Hercules air defense system, since there was a time to react and prepare thanks to the length of the recon operation. That system could have shot down the MiG-25 as well. In hindsight, this was an entirely unrealistic assumption. The Nike Hercules system was primarily designed to operate with nuclear warhead, although conventional warhead was available for training. From an American perspective, transferring such a system for a relatively minor, we can say hookers issue simply was not worth the effort and diplomatic and political issues. Especially since the Nike Hercules was already being in retirement phase in 1971 and 1972. Perhaps the assumption was based on the idea that since the system was no longer needed, it could be theoretically be handed over one battery with limited missile inventory to Israel. The Israelis attempted to intercept and shout down the MiGs using Mirage 3 and F-4E fighter jet as well as the Hawk air defense system, but those efforts were unsuccessful. Another conflict in which the MiG-25RB was participated was the prolonged war between Iraq and Iran from 1980s to 1988. As the war dragged on, both sides began targeting each other's economies, aiming to reduce revenues from oil exports. The MiG-25RB took part in such operations, including the bombing of oil storage facilities and the port on Kharg Island. The island is located near Iraq's southern border. Iranian oil storage infrastructure was built on the island. The core of the facility consisted of storage tanks approximately 124 meters in diameter, each placed within its own containment basin. The 1 by 2.5 km sized Kharg Island was suitable target for the MiG-25RB's navigation and bombing system, which had a targeting error of ± 820 meters along the flight path and ± 1700 meters in lateral direction. The attack flights were launched from the Nasiriyah airbase. 3 MiG-25RB aircraft were prepared for the mission, with serial numbers 114, 141 and 120. The operation was planned with active involvement of Soviet advisors. All tasks were carried out by Iraqi officers under their close supervision. 3 sorties were planned to destroy the oil storage facilities. The first mission was flown by the airframe with serial number 140, carrying 4 500 kg bombs. The bombs landed with a small dispersion but missed the target center by about 1 km and by 800 between 1000 meters to the left. Based on this, specialists adjusted the computer data and the second bombing run had a smaller error. During the second attack, the bombs hit a tanker ship anchored near the shore. After further considerations, the third mission resulted in 3 hits in the oil storage facilities. This operation clearly demonstrated the limitations of the MiG-25RB using conventional bombs. Essentially, even attacking a target size of an airfield was not feasible. It was only suitable for bombing large industrial complexes or cities, effectively terror bombing. However, with a nuclear bomb, the accuracy of the bombing system was considered sufficient. People often compare the reconnaissance variant of the MiG-25 and the American SR-71 Blackbird due to their high speed and similar mission profiles. However, this comparison is frequently based on the urban legend that the MiG-25 is unconditionally capable of reaching or even sustaining Mach 3 speed. Now we know the statements like these are not true. As we have seen, the MiG-25RB could theoretically reach Mach 3, but only under many specific conditions, and even then not for sustained flight. The typical operational speed for the MiG-25R and RB was Mach 2.35. In contrast, the SR-71 could maintain Mach 3.2 indefinitely even under standard atmospheric conditions, only the fuel was the limiting factor. Compared to the almost entirely titanium-built A-12 and SR-71, the MiG-25 was built mostly from heat-resistant steel. It was a far simpler aircraft. The quality difference of the American and Soviet aircraft is clearly visible in their range. With nearly identical, about 15 tons of fuel load, the SR-71 could fly about 10% less distance than the MiG-25RB, despite flying 35% faster. Considering that aerodynamic drag is in general increases with the square of the speed, this is a massive difference. The SR-71 with slightly more fuel with a slightly heavier airframe could achieve and sustain significantly higher speed with almost the same range thanks to its sophisticated engines and polished aerodynamic. This was a sharp contrast compared to the MiG-25RB with its protruding bolts, misaligned panels and massive but rudimentary engines. On top of that, the Soviet reconnaissance aircraft initially had an unreliable navigation system, which operated with a far greater error than its American counterpart. However, it's also important to remember the design philosophy behind each aircraft. The MiG-25 was part of a family produced in 1000 scale. The reconnaissance variant and the BM variants were just smaller branches of the family. Due to the massive production volume, it was simply not feasible to achieve the kind of artisan-level quality, essentially custom-built standards. The SR-71 was built almost entirely from titanium alloys instead of heat-resistant steel alloys, which made the Blackbird family far more expensive. Thanks to this, only 15 A-12 and 32 SR-71 airframes were built, about 20 times less combined compared to the MiG-25 family. The price difference of aircraft was also a strong indicator of their complexity. The export price of the MiG-25 PD or RB was 15.4 million rubles. The MiG-23 MF cost 7 million rubles. The double price of the MiG-25 is understandable for nearly twice as heavy twin-engine aircraft. For comparison, the twin-engine SR-71 cost $34 million, which can be compared to the contemporary twin-engine F-4 Phantom fighter family. In 1965, the F-4C fighter cost $1.9 million, and the future F-4E variant was estimated at $2.4 million. The SR-71 was about 15 times more expensive than the only American twin-engine fighter in production at the time. I think these figures clearly explain what the SR-71 and MiG-25 were. The first was a state-of-the-art airplane, the second was a mass-produced fighter with the usual Soviet quality. They cannot be mentioned on the same page. If you like the video, you can share, like, subscribe or link the bell and follow the channel. You can support it via Patreon or YouTube channel membership for exchange for early access, voting on planned topics, extra content and updates about the project. So far 18 extra content has been released, their description are the link under the video.